Okay, so I got the recording started again. Hopefully you guys saw that. Now I'm going to share my slides. Okay, you guys seeing my slides? Okay, perfect. Okay, that was a new one, guys. I've not had that occur before. You guys were. Let's see here. Let me open up chat too, just in case anything on there. Okay. Okay, I think we're back to where we can function here. Let me get us caught up on where our slides are at, and we'll be good to go. Okay, that look right? Is that where we were? Okay. All right, well, let's hope that does not happen again. That was weird. Okay. All right. So as you guys mentioned, the last thing we said was 20%. So just real quick on this slide again, to catch us back up again, remember the 20% rule on all of these in terms of being within range when you measure your dose or measure your QC every morning. Again, battery calibrated annually. Those are, I guarantee those are questions on the test. Okay. All right. See if I can get back on track. Okay, so now we're moving on to dose calibrator. um, okay, so dose calibrators, you guys have probably all used those. You've probably all done QC on them, so these are pretty familiar. I know that in a lot of places, one of the first things the techs have you do as a student is like, go do the hot lab, right? Learn all that. So again, this is used to assess the amount of radioactivity in a radiopharmaceutical prior to administration. This is going to operate in the ionization saturation region. So again, it's a gas-filled chamber, has a cathode and an anode, functions as the radiation causes current, just like what we've been talking about. It depends on the amount of activity and the type, like we've also talked about. Now, the thing different about the dose calibrator is obviously you're going to be measuring different types of doses, right? You'll be measuring I-131, you might be measuring iodine, whatever you're doing, right? So you're going to have a difference. If you just stick it in there and you get a reading out, you're going to need to know what that means. So what happens in a dose calibrator is there's electronics within the system that takes whatever voltage that it's seeing, whatever that current is, and it applies a factor for each radionuclide. So when the dose calibrator is first set up, it's going to go in and it's going to ask you what types of radioactivity you're using. So that's why you have all the different buttons on your dose calibrator, right? All these buttons right here are functioning to say which types of radiation you're using or which types of nuclides you're going to use. For each of those nuclides, there is a factor applied to the current that is seen. So if you didn't have a factor application, you would get a current, but it would be the same. And as you can imagine, you might have some tech, and let's say you have 20 millicuries of tech and you put it in there, and it's reading 20 millicuries of tech, and there's a certain amount of radiation coming off that. And let's say you took like 4 millicuries of I-131, and because it's in the 360 range, it's going to read as though if it was only on tech, it would read as a high amount of tech. It might read as 20, 25, 30 milligrams of tech if you had it on that. Because again, it doesn't just see the amount of radiation, but also the strength of that radiation causes more ionization. So that's why you have to have the different buttons. Otherwise, the readings would be off. So the important thing for you to think about here, you don't necessarily have to understand the electronics of that. Just know that there's a factor that's applied to each of those to get them in the correct range. And then for you as a tech, you just need to make sure you're measuring your dose on the right factor, right? If you're measuring tech, make sure you hit that button on tech so that factor can be applied. And that's part of the calibration of the dose calibrator. We'll talk about QC for it in a minute, but that's part of the calibration that's done on a dose calibrator when it's installed, and the factory, but also a physicist and things will look at those things and make sure that they're correct. And we'll talk about that in a minute. but that's essentially what it's doing. Now the NRC, which is the National Regulatory Commission or Nuclear Regulatory Commission, requires that any radioactivity administered to the patient be assayed in a dose calibrator. Okay, so you have to measure your dose. That's by law. That's the law that we're under. I have actually worked. I worked in a place here in Ogden for a little while, and there was a tech that would not measure his doses. The doses would come from the radio pharmacy, and it was 20 millicuries for a bone scan, and he wouldn't measure. He would just be like, "Oh well, pharmacy says it's 20. I'm going with it." Don't do that. It's against the law, and you need to measure because the pharmacy can make mistakes. Mistakes can occur. You can grab what you think is tech, and you might have grabbed something else. And so it's important to go through that process of measuring, and it, of course, is by law. So now the NRC requires also that it be calibrated in accordance with nationally recognized standards. Again, this is what I was talking about. Manufacturer will have that. There's two organizations that kind of do calibration for dose calibrator testing. It's the American National Standards Institute and the American Association of Physicists in Medicine. So you'll probably have one of these institutes that is in charge of doing and going over the calibration for your dose calibrator, and it has to be within those standards. So we'll kind of mention now the QC on it and what I'm talking about with some of those first things. But the first one, which I kind of started to mention, is accuracy. So you have accuracy, constancy, linearity, and geometry. So accuracy, what they do is the National Institutes of Standards are going to give you sources that come with your dose calibrator. And you've probably seen those. It's likely cobalt or cesium. And the National Institute also has sources. So if you send your dose calibrator, if you ever send your dose calibrator out, typically you don't, but if it needs like repair, you may send it out. And so they'll have sources that they use to calibrate as well. But essentially what happens with accuracy is they just take those national standard sources and what they're supposed to be at, and then they take every channel on your dose calibrator and they compare them to those sources, and they calibrate that activity compared to what the decay should be. And so 10%, anything out of 10% range is going to require an action. This is done annually. Most of the time, a physicist is going to come in and do this. I think one time I had someone tell me that their techs did this. That's not typical. Most of the places you work at, your accuracy that's done annually will be done by a physicist that will get in and do it. Constancy is the next one, and that's one that you are going to do. And constancy is performed daily. And again, remember these things right here, like the daily, the accuracy is done annually, that constancy is going to be done daily. Those are questions on the boards, easy, right? So constantly is done daily. This is used to verify that the dose calibrator is just measuring accurately what it's supposed to measure. So again, you usually have your two sources. You have cobalt and cesium. Those are the most common ones used. And you basically just have to do daily measurements on every one of the channels. This is kind of your quick daily measurement to make sure. And essentially, you've done this before. I know you have. You put it in there. You get a reading. You're going to take that reading and enter it into your computer. And again, just like with your meters, somebody has taken the information that came back and with your dose calibrations, that you should have documentation on your dose calibrator of what those readings should be. And that's been put in your computer as an easy way for you to check. But you put them in the computer and they have to be within a percentage. Again, 10% is going to be the trigger on these as well. But you perform it daily. And so again, you're going to click on each one of those channels. That changes the factor, and it should match what's expected on the cobalt and the cesium. And that's just to make sure that your camera over time is just not varying and it's reading that and being constant, right? It's an easy way to remember it, constancy. The next one is linearity. And what this does is it's a measure of over the range of activity that your dose calibrator can look at. Is it able to accurately measure whether you have a small dose or whether you have a large dose? And can it calculate the ability to know what a dose should be over time? Okay. And so the way this works is usually it's like a tech source. And what you'll do is and a lot of times this is done by a physicist, but this can be done by a tech, like some of your techs may do this. But you take a source and you know the radioactivity of that source, and you're going to measure it, and you'll measure it throughout the day several times, and it's going to take a reading, and then you enter that reading into a computer. And essentially what it does is the computer has a kind of a logarithmic graph. And what the computer does is it says, okay, I know what the dose is at this certain time. And then it applies the math, just like you guys have been doing. It does the radioactive decay. And it says, okay, at 3 o'clock and at 4 o'clock and at 5 o'clock and at 6 o'clock, it should measure at this according to the math. And so when you put it in your dose calibrator, you're seeing, is that the case, right? So you might put it in at noon, and you might put it in at 1 or 2, and you might put it in at 5 or whatever. And then you're going to take those 2 or 3 daily measurements and see if the radioactivity or the decay is matched by what the math expects it to be, okay? And that's performed quarterly. There's one other way that this is done. I've seen at our place, a physicist does this. We don't do this. But the other way they can do it is they have essentially these tubes, and the tubes are a large tube, a smaller tube, a smaller tube, and there's several sets of these tubes. And it's kind of like if you've ever seen those Russian nesting dolls. It's like the doll within the doll. You take it out, and there's another little doll inside, right? So it's kind of like that. And so what they'll do with that is they'll take the first tube and they place it over the radioactive source within the dose calibrator and get a measurement. And then you place another tube in that covers the original tube and get a measurement, and then a third tube. And each of these tubes is decaying or measuring a decay because it attenuates a little more. So it's like you're creating time out of just attenuation. And so if their dose calibrator, there's an expected of what that dose should be based on how much of that attenuation is in the way. So that's kind of the same idea of if the dose is getting smaller, again, can you accurately assess a dose across a large range of activity and time of activity, okay? So that one is performed quarterly. And again, when I think of it, I just think it makes sense. It's called linearity. Is it able to do something over a long line of activity? Linearity, right? Just like constancy is it constant over time? And then the last one is geometry. And geometry determines whether activity may or may not change depending on the sample volume or the container of that volume, okay? So, for example, most of you probably use your pharmacy probably sends you like your doses in 3 millimeter syringes, right? And you may have doses from, half a millimeter to, or not millimeter, half a milliliter to a mil or whatever, right? Your doses range in size, but they're always in that 3 ml syringe most of the time. And so what's happening here is that this is a measure of how well your dose calibrator is able to measure, depending on if we're looking at a different size or shape of container that it's in. Again, you set that dose down inside the well calibrator, and you're putting it down inside the dose calibrator. So you're putting it in a area that's the gas-filled detector, right? And so the question is where that is within that tube, does it matter? Does it make a difference? Can it read it no matter what it looks like, or the size and shape of that vial? This has to be performed when your system is set up, they'll perform it, or if you have a big change in vial configuration. So like I said, most of the time when your dose calibrators were set up, they were probably set up to look at 3 millimeter vials, and then also, or I keep saying millimeter, sorry, 3 milliliter vials, and probably maybe 5s. A good example of this is at my facility, and this is when I was working more in general nukes, but we do a treatment called TheraSphere. Maybe some of you have seen some of those. When we initially started doing TheraSpheres, TheraSpheres come in kind of a short, stubby vial. And so they actually did this on our dose calibrator. They did the geometry, and they measured, and they changed the vial and the configuration to make sure that it was measuring accurately. But no matter what shape your vial is, essentially what they do for the test is they'll take that vial and they put radiation in it, and they know the amount. So say you use tech and you have 20 millicuries in there, they'll start with 20 millicuries in a very, very small amount of saline, and then they'll keep filling it up. and measure until it's about, on the books it says 67% full. And basically what you're doing is you're measuring if it stays the same radiation level, even though you're increasing the volume or the amount that radiation is dispersed in between. So again, geometry, it's just size, shape, how it looks. Can the dose calibrator keep even with all that? Okay. Any questions on those? Okay. I included this chart. This is just an awesome, nice chart for memorization purposes. I loved it because of this right side where it talks about frequency. Because again, I can just guarantee these are test questions right here. And so again, accuracy annually, constancy is going to be daily, linearity is quarterly, and then geometry is when there's a setup or when there's a massive change in syringe or vial configuration. Okay. So memorize that. Okay. So that is it with gas-filled detectors. That's all we've got for gas-filled detectors. Any questions gas-filled wise before we move on to anything else? All right, I'm just boring the heck out of you guys today. No, just kidding. All right, so let's see. How do you guys feel about taking a quick couple-minute break? If anyone needs to run to the bathroom or anything like that. We had a little bit of a break while I tried to figure out everything, but I don't know if any of you went anywhere. Does anybody need a break? If anyone's in an overwhelming need for a break, we'll take one. If not, I'm fine continuing. I'm not seeing any heads shaking, and I'm not hearing you guys say anything. Okay, cool. Looks like you guys are talking about, I just noticed on the chat, you're talking about some of the softwares you use for doing QC. So yeah, there's a bunch of different types of software that you'll have on your computer for entering all your QC data and keeping track of that. So cool. Okay. All right, let's talk about well counters now. So a well counter is a scintillation device. And remember I mentioned when we talked about sensitivity and efficiency, I talked about how radiation goes in 360 cubed, right? It goes out in all directions. And remember when we had our discussion about gamma cameras, we mentioned that if we were able to gather, the sensitivity is dependent on how much radiation is coming off versus how much are we able to gather. And I want you to remember with gamma cameras, it was very small. One reason is because the gamma camera is only in one direction. And then the other reason is that we had to do those boreholes, right? And collimators in order to be able to get an image out of it. We had to cut a lot of that out. And we were down to like, I can't remember what the number is, but it's like 0.1% or something like that. So not super sensitive, not super efficient, but we have to do it to get an image. Well, with a well counter, we kind of throw away all of that and we go for super sensitivity, right? We go for being able to measure a dose because in a well counter, you're going to measure things that are very small. You're trying to find very small amounts of radiation. So things like your wipe tests, right? You're wiping your dose when it comes in, you're wiping countertops and things like that. So we're looking for tiny bits of radiation. So we need something that's really, really sensitive. And that's what a well counter does. So what they've done with a well counter is it is exactly like your camera. It's a crystal with a photomultiplier tube and a preamp. So it works the same way. But what you'll notice here is they actually bore a hole down into the crystal, okay? So this is about as efficient or as sensitive as you can get because almost the entire dose is surrounded by the crystal. You've got one little bit, just the hole up top, right? So only one side. Your gamma camera, we only saw one side. Now we're surrounding everything but one side, and we're not trying to cut out the radiation in any way using collimators or anything else, right? So this is really, really high sensitivity. So because of that high sensitivity, we can get down to the nanocurie level and we can detect radiation super, super, super small. Okay, so that's why your well counter works for those things like wipes. Now, because of that high sensitivity and high efficiency, that limits the amount of activity to about 1 microcurie. So what I mean by that is that you can only accurately measure up to about 1 microcurie because if because of the sensitivity and how much we're gathering because of the surrounding geometry, when you get much above about a microcurie, you're just overwhelming, and it will see an activity. If you put something higher than microcurie in, it would give a reading, but it can't be accurate because the system can't gather the data fast enough because there's so much that it overwhelms, right? So you're getting kind of a paralyzed type effect. So you're getting a reading, but you're not getting all the reading. Some of that is just not seen because it'll overwhelm the system because it's so sensitive. So again, remember this. This could be a question I would see that, what's the max amount that you can use or accurately measure in a well counter, and that would be about a microcurie. Again, remember, super sensitive. This is for looking for really small radiation sources like wipes and things. The other one that this can be used for, if you've ever done, there's a test where you can look at nasal, if there's nasal issues, they can have like leaks from brain cavity to nasal cavity. And what they'll do is they'll give a radio source, and then they'll put pledgets up inside the nose, and it's supposed to absorb any leakage coming through. And then you can take those pledgets. It's a really gross process if you've ever done it. They shove it up the nose, and then they have these strings coming out, and they're all labeled. And then your job's going to be to pull those out and go measure those. It can be kind of nasty, but that's one of the ways we use a well counter, because again, we're trying to just find any detection of radiation coming through from leaks in those sinuses. And so that's one where we use this on a test. But most of the time, it's like your wipes and things like that. Thyroid probe is the other one that we'll cover here. And again, this works the same way. Again, a thyroid probe is a scintillation device. And so again, what we learned on the gamma camera applies here again, so I won't get detailed, but you have your photomultiplier tube with the crystal on the front, preamplifier on the back. Unlike the camera where we're gathering data to create a picture, this again is just going to give you counts, right? Because you're counting the thyroid. We're doing this for either I-131 treatment preparation, things like that. You'll notice actually that the thyroid probe does have collimators on it. These two are called collimators. However, the question I put here is why wouldn't you image with it? And that's because, again, that's a really big, it's basically a single bore, right? It accepts everything that comes in. So you can't create an image off that because that bore is so large, you're just going to get a lot of light. So we can't create an image. If you were to take and add small bore holes across the front of this, many of them, you could conceivably maybe find a way to get some kind of imaging off of it, maybe in theory at least. But again, we can't image with the thyroid probe, even though it's a crystal photomultiplier tuner preamp, because it's just one borehole. And again, it's just for counting. Okay. All right. So that's pretty much it for the ancillary equipment that we're going to cover today. Any questions on any of that you're thinking about right now? We're going to move on to another topic, but I want to make sure we kind of cover anything that we talked about previously. I don't see anything in the chat. Okay, so this is where we're going to get into our discussion about statistics. And I don't want to bore you to death, but what we're going to start with is we need to have, and some of you may have taken statistics and some of you maybe haven't. This is going to be basic. I'm going to cover a few basic statistical principles, and then we'll apply them and talk about why they matter in nuke med. And I know that it might feel kind of boring at first. I hope not to bore you to death. I'm going to try to ask a lot of questions, so I'm going to try to do more questions than I normally do to try to move this along. And so would love your participation. But just trust me for a minute while we learn some of these basic statistic principles, and then I'll give you a payoff that's very applicable in nuclear medicine and why we care about statistics. Because in the end, in nuke med, our accuracy and our ability to be able to do what we do actually depends on statistics. And so we'll show you why. And this is, they talk about this being required for boards. So what do you do, right? Okay. Make one of my screens a little smaller so I can see you guys. Okay. So the first thing just do. You guys can still just see the one screen, or do you see two screens? I just all of a sudden got two screens. Double screen mode. I have no idea what that is. There we go. Got it back. Okay. I'm assuming we're good and you guys see one screen. It's a struggle fest today, you guys. Gosh. You're gonna fire me. Okay. So I wanted to go over this again. I know I've shown you this multiple times, but when we talk about statistics, the statistics that we're going to be referencing in nuclear medicine are counts. So I wanted you to remember again that when we talk about radioactivity, we talk about radioactive decay, when we talk about imaging and getting counts, we're just simply talking about, again, those tight packets of energy, right? So it's important to remember as we talk about this, we're just talking about a way to measure energy in those tight packets of energy.
I gotta interrupt you real quick. I can't see anything.
You can't see anything?
Not your shared screen. I see you, but not the shared screen.
Okay. Thank you for interrupting me. Man, I'm having technical difficulties today. Let's try this again. It was funny on my end, all of a sudden it showed two shared screens that were the same thing and I couldn't see you guys anymore. So I thought I was just shutting off one of them, but maybe I shut them both off. Can you see now?
Yes, I see it.
Okay. Thank you for interrupting me.
Of course.
Okay, let me just adjust here. Okay. So again, remember that. I've shown you this one multiple times, right? Okay. So let's get into some principles here. So the first thing I want to talk about is precision versus accuracy. Okay. So when we talk about precision, precision is the spread or the range of reproducibility of data. So when we have small precision, it means that there's little variation in whatever data we're looking at, and that equals predictability. So for us, we're going to talk about counts, the amount of counts that we get, and the counts we are required to get in nuke med. And so when we talk about counts, again, more counts is precision. When we talk about reproducibility, if we have small variation in what the counts look like, then we have reproducibility. And the other one is accuracy, or how close to the true answer or gold standard are you? Okay, so spread of data versus what we're after or what we're trying to get to. Let me give you an example to make this a little more sense. Okay, so I have a 9mm handgun, right? And I will go and I'll take that handgun and go to the range and shoot. When I go shoot at the range, I take and I look down my sights and I'm aiming for that bullseye. And what typically happens for me is I end up with a spread that's up and to the right. So it's up and to the right. However, my grouping is really tight, meaning that of all the shots I took, they're fairly close together in the grouping, but they seem to always be up and to the right. So here's my question where I need participation. Am I precise and am I accurate? What do you guys think?
Not accurate, very precise.
Okay, who was that? Lewis? All right.
Yes.
Hey, Lewis. Thank you for being brave here. So, and you guys can help Lewis, but I'm gonna ask this directly to you, Lewis. Why do you say that? Oh, I think you're muted.
I was just thinking that gold standard, so that's the bullseye, right? You didn't hit it. So I would assume you were not accurate.
Okay, absolutely.
And I guess in this case, your groupings were very spot on. So there's little variation. So
Yeah.
you're very precise in that.
Amen. You guys agree? You guys agree with Lewis? Okay, I'm seeing head shakes. Yeah, exactly, right? So there's an easy way to see it. I didn't have much of my precision was good because there's not a huge range. The range is tight, right? Small precision, little variation in the data. So, and then my accuracy, though, is not great. So we have some predictability in my precision. Like if you had been to the range with me several times, you'd be like, I know what Mike's going to do. He's fairly predictable because of that precision. but I may be predictable, but I'm not very accurate. Again, I'm not getting what I'm after. So these are going to be two things we kind of refer back to as we're talking about why statistics matter in nuke med. Okay. I'm going to give you kind of four reasons, and then we'll get into explaining those. But here's why: four reasons for statistics in nuke med. So one of them is that radioactivity is a random process. Now, what do I mean by that? Well, think of when you have your survey meter and you're trying to detect radiation. And let's say you have the audible setting on, or even if you're just watching your meter, it's going to be like beep, 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 right? You're going to have, it's random. It comes in random. So our counts are random. They're not perfect. Now that might seem counterintuitive because I know that as we talk about radioactive decay, we can say, okay, I know what it'll be at 3. I know what it was at 10 o'clock. I know what it'll be at 3 o'clock. So over the long scale, it's radioactivity happens in a predictable way, but it's random in its current activity, right? It happens as a random process, but again, we can look at it over time and know how much the decay will be. So it's constant over time, but random in its process. Okay, so because of that, we need statistics to look at anything with random nature. You're not going to have exactness, and you need to have statistics. So the second one is statistics can affect diagnostic accuracy, and we'll show you why that's the case. Statistics can also affect image quality because, again, we have to guarantee we have enough counts to make an image and the quality of the image. And then statistics are also used to measure machine accuracy, right? The only way we can know our machine's accurate is if we gather enough statistics about how it's functioning, okay? And again, all of that is because nuke med is a random process. Radioactivity is random. Okay, so let's look at three things we need to know to understand how this works and why it matters. One of them is mean. And you guys have probably done mean before, like probably, starting in junior high or whatever, you learned what mean is. But mean is the average group, it's the average of a group of measurements. So you would take, a group of things and you calculate that by adding them together and then dividing them by the number you had, right? So if you had 10 measurements, you'd add all those measurements up and then you divide it by 10. And that basically just gives you an average, right? It's kind of the basic average. You guys have probably dealt with that again since you were young. Standard deviation is the next principle, and standard deviation is a measure of the spread of data points from that center average. Okay, so this is how much data points. So thinking back to the holes in my target, right? If standard deviation is a measurement of how much was that spread? Was it a tight, so a small standard deviation, a small number in my deviation, or was it spread out in a large number in my deviation? Okay, so this is the measure of precision of the data, the spread of the data. And then the other thing that we'll look at is called coefficient of variance, or sometimes it's called percent standard error. And this is just the error that is to be expected in the data. Again, because of the randomness of radioactive decay, we're never going to get perfect, but statistics gets us predictable and close, right? So what's our percent error? We can actually calculate what the error is, and you'll see why that makes a difference as well. Okay, so I want to do another example so that we're not just randomly talking about weird principles. Let's talk about life insurance. So I'm 47, and if I had to get a life insurance policy today, I could probably get one. It'd be okay, right? I probably wouldn't get like the best deal in the world, but I could probably get an okay life insurance policy. But I started my life insurance policy back in my early 20s. And I got a great deal then, right? I got a way better deal. And if I waited till I was 60, the chance of even getting one could be probably low, or if I do get one, it's going to be a really, expensive, terrible policy. Why? Why is that?
I guess it's all about risk. They don't.
Yeah. Yeah, risk. What do you mean? What do you mean by that? Like
the at 60 plus, you're higher risk to have something grave already or acquire something soon than when you were 20. So the insurance is going to charge you a lot more because they're assuming more risk.
Yeah, exactly. You're exactly right. Like the risk is pretty obvious, right? Because when I was 22, like the likelihood that I'm going to die is just really low. Like, yeah, could I get in an auto accident or something? Sure, I mean, that can happen, but I'm not likely to have a heart attack or a stroke or have something that is that way, right? Because I'm not old, I'm young. It's pretty obvious. And so they have a way of saying, okay, who is at high risk or who's at low risk, and can we insure them? How do they know that? Because it's not a guarantee. Like, how do they know that they can rely on that idea?
Data,
What's
I
that?
guess. A bunch of data that they've gathered, I guess.
Data, right, right, exactly. So do life insurance companies deal with five people? No, right? They deal with hundreds of thousands, and they have the data, right? And that's where statistics helps life insurance. Is they gather enough data. You gather enough data, you can start to see patterns within that data, right? And so then they can make probability and predict what may or may not happen with fairly good confidence. Another quick example, and then we'll kind of gather that into what we're talking about. If we took 5 pennies and we tossed them on the table, as you can imagine, sometimes we would get like 3 heads and 2 tails. Sometimes we get 2 heads and 3 tails. That would probably be most likely. It would probably be really unlikely to get 5 heads or 5 tails all in all pennies in one single toss. And so if we did that a few times, it'd probably be hard for us to determine or guess what the next roll would be. But if we did that 100,000 times, we would start and we graphed that, we could start to look at predictable patterns in what we would get. Okay. And that predictable pattern graphing is what's called a Gaussian curve or a bell curve. You've probably heard of this before. Okay. So in a bell curve, the center represents the mean or the average. And like with our pennies, it's likely that we'd probably have like this kind of area within here is probably going to be like 2 heads, 3 tails, or whatever. And then say going off to the right, all the way down here is probably where you're going to get all heads. And on this other side is where you're going to get all tails, right? And the likelihood is more or less. So on a bell curve, we have what's called one standard deviation. One standard deviation represents the spread at 68.3%. So if we took our data and we actually did the numbers and calculated what 68.3% of it is, that would represent one standard deviation. And that would show us a measurement of how big our spread is. At 68% of the data, how wide is our spread? If you went 2 standard deviations, you would be covering 95.5% of the data. And if you did 3 standard deviations, you'd be covering 99.7% of the data. What that essentially means is if we had a curve like this and we saw our penny representations on here, we could say, I can guess with a 68.3%, if I look at everything within one standard deviation and I look at what those like 2 heads, 3 tails, whatever, I could guess right 68.3% of the time. If I was using one standard deviation, I would be accurate, right? Because I would include all of the data within that. If I wanted to be able to guess or my probability increase more, if I want to be more right, I can include more of the data. And so I could be right if I said, well, most of the time I'm going to guess next time it's going to be 3 heads, 2 tails, or 2 heads, 3 tails, or 4 and 4. Then I'm going to be right even more. But again, I might not be as accurate. The less data I have in here, I might be more accurate if I look at smaller numbers. But the more I let in, I'm going to be able to guess it, but it could go smaller. Okay, so that's kind of how you look at these standard deviations. Now let's look at actual numbers of how standard deviation is calculated. And what you're going to see is as we look at more data, what I want to get to is as we look at more data, we become more accurate. And we'll do that with the next two principles, okay? So the way standard deviation is done for counts. Now this is different for other types of statistics, but for us, where we're just talking about a single number of a thing, in our case, counts of radioactivity, the standard deviation is equal to plus or minus the square root of the counts. So what that means is if you turn on your camera and you got 100 counts, to figure out the standard deviation, you would square root that 100, which would equal plus or minus 10. And so what you're including in that standard deviation is from the number 90 all the way up to 110. Okay, so that's one standard deviation. If you did two standard deviations, you would do the same thing, but you would multiply by 2. So it'd be 2 times the square root of 100. Square root of 100 is 10. So when you do that, you get plus or minus 20. So your range gets a little bigger when you're willing to look at those two standard deviations. So that's 80 to 120. Okay, so that's how a standard deviation is calculated. Now let's look at how percent error is calculated, and then I'll bring those two together. So coefficient of variance or standard of error, again, remember this is the error that's expected because we're working with random things that aren't always perfectly predictable. And so percent error is the square root of the counts divided by the counts times 100. Okay, so in the case of our example we just used, if you take 100 counts, you do the square root of the counts, which is 10, divided by 100 times 100, you get 10%. So with 100 counts, one standard deviation is going to give you a 10% error. So you're only going to look at that 60, you're looking at 60% of the spread of your data, and you're getting a 10% error there, okay? Here, you're doing 100 counts, and we're doing 2 standard deviations. And so again, the 2 times the square root of the counts is 20, and then divided by 100 times 100 gives you a 20%, okay, 20%. All right, now let's see if we can connect these two principles. So if I do 100 counts and I do 2 standard deviations, and what this means is that means that 95% of the time I could by probability guess how many counts there are going to be, right? Because I'm looking at more data, so it's more likely that I'll be able to guess it accurately. And so we have a range from 80 to 120. So anywhere within that range would be accuracy. And if we do the percent error, it gives us plus or minus 20% error. Okay, so that's 100 counts. Okay, so we have 100 counts. We're pretty solid that our data is accurate, but we have this kind of high error rate. Now, what if instead of 100 counts, because we never do 100 counts, what if we do 10,000 counts? Well, 10,000 counts at 2 standard deviations gives us 200 in our range. So our range now goes from 9,800 to 10,200. But look at what happens with percent error when we do the math. It goes way down, okay? So this is what I want you to connect. Lots of counts. We can still remain within our accuracy probability, and our error goes way, way down. Okay? Way, way down. This says kind of the same thing right here. Error goes way down. So this is what I want you to think about. If you guys do let's say we're doing a bone scan on knees, right? So you do a bone scan on knees and you throw the patient under there. What are your hospitals doing? Do you count to time, or are you doing counts? Tell me what you do with the knee for just a static and anterior image? Somebody be brave. What do you do with the knee?
I mean, we do to time for our bone scans.
Yeah, you do time. So how much time do you do?
Depends on the scanner we're using, whether it's GE, Siemens, or any of those other types of things. But
Give me one of them just for
like
example.
7 minutes.
Okay, so you go 7 minutes. So you can do 7 minutes. Does anybody do it based on counts? Thanks, Ashley. Anybody else? Probably. There's some places I can see like they'll do time or you'll do counts, or some places will put both on, like whichever comes first. Yeah, okay. Someone said in the thing both. I just also noticed somebody put insurance companies more like corrupt. That's funny, Bethany. Yeah, okay, so you do counts or time, right? Now, you've all done a bone scan, right? You've put them under there, and you can see on your screen that it's starting to gather counts, right? And you're watching it. So you said, Ashley said they go 7 minutes, all right? So, Ashley, I would imagine, I know for me when I've done bone scans, we used to do, I think, 5 minutes on some of ours, but after about 2 minutes, can you see the bone scan pretty well? Would you agree with that? Yeah, I saw your head shake. Yeah, like after 2 minutes, I can look at the scan and I'm like, hey, this looks pretty good, right? Like it looks pretty good to me. Like I don't have a problem with it. I can even maybe see some pathology forming there. I can see some areas of uptake. So my question is, why not just be done and increase your patient throughput? After that 2 minutes, why go to the 7? Why not just be done?
Generally because it creates better images when you go longer. The pathologies will be able to show up brighter because sometimes, like, just because the bone's closer, it'll be emitting more counts. It doesn't necessarily mean there's a pathology. Like, if you're looking at the pelvis, like the top of the pelvis on the anterior side is going to be hotter, and then on the posterior, the sacrum will be hotter, but that doesn't necessarily mean there's anything there.
Okay.
So you go for the longer to get the full measure of counts to actually see pathology versus just what's close.
Okay, awesome. Like that, all that is absolutely true. Um, but then I would ask the question because nothing's wrong with what you said. But then why not do 15 minutes? If we get a better image, why not go 15? Why are we doing a certain amount? Any ideas? Think about what we just learned here. Oh, it's Jesse. What you got? What you got there? Jesse, drop error percentage. Diminishing returns. Yep. So two things, and you hit them both, Jesse. So one thing that happens is if you count forever, you're gonna get a diminishing return, meaning that once you get a certain amount of data, the more data we gather, just like I showed on here, the more data we gather, the percentage of error goes down, right? And again, because nuke med is random, we're working with random counts. It's not perfect. It's not like a CT scan where we get these nice lines. We're working with the random nature of something. The more counts we gather, the percentage goes down. Now that gets to a certain point where it levels off and we get diminishing returns on that. So that's one reason we don't go forever. But the other reason is that when a radiologist reads your bone scan, and some of you may not have realized this, but on the report, it's going to say that they read the bone scan to the level of 2 standard deviations. What that means is that the radiologist is saying, my interpretation on here, based on the data, I'm giving the probability that I'm 95% accurate in 2 standard deviations. Now, the only reason he can do that, and he's dependent on what you do, is because your protocols have been set to a certain number of counts or time. And what that is it's guaranteeing that you have enough counts that the percentage of error is actually really, really, really low. So even though at 2 or 3 minutes, I probably have a good bone scan, and a radiologist probably could look at those knees and he probably could make an assessment of what's going on. However, for him to actually be accurate on his report that he's reporting 2 standard deviations, 95% probability, your protocols have been set up for the numbers to statistically guarantee that he has accuracy in what he's looking at. Okay. So again, I realize this is a long discussion for what might feel like a small payoff, but that's why in nuclear medicine, we care about counts. That's why you have protocols. That's why if they set it to counts or time or whatever it is, they're doing that so that they can guarantee the accuracy of what we do. And really in nuclear medicine, we don't have anything else to guarantee our accuracy besides statistical data on number of counts. So this is one of those things that will make you a good tech. You can get away with doing a 3-minute bone scan and probably get some okay images to the eye, but you need to be good techs and be accurate in your data. It's why you have the protocols. Those are kind of two things I see happen a lot. This is something I see techs do a lot. And don't get me wrong, there might be times where you have to end the scan early. Maybe a patient has an issue. We have to work with people. and patients. So again, it can happen, but if you have a patient and you can go get the full counts that you should or the full time that you should, this is why you're doing it. Do it. Be a good tech and do it. The other one is what I mentioned last time, which is get your detector closer to your patient, right? I see lots of techs that'll keep it way off. The closer you get, the more counts you're gathering, the better picture you get, okay? But this is essentially why, really the main reason why we care about statistics in nuclear medicine. And again, I just included the percent error thing here. And again, this is what's interesting is with 10,000 counts, 100 counts, going from 100 counts to 10,000 counts, we brought our error from 10 to 1. But we don't even do 10,000 counts, right? You do like 500,000 counts or 750,000 counts. So you could, if you did the math there, now you're down into the 0.0 whatever percentage range, right? So you bring your percentage of error way, 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 way down, and you guarantee the accuracy of those images. Any questions on that? I'm going to share a couple more things, and then we're basically going to be done. But any questions on that idea and those concepts? Okay. Colton gave me a head shake no, so I'm going with it. Thanks, Colton. All right. So the other thing I want to show you, and then we'll get to talking about what's called chi-square, which is listed on your boards. We did the standard deviation equation I showed you a minute ago, which you're not necessarily going to have to be able to figure out standard deviation, so don't stress about that too much. But this equation is a standard, that was just for single counts. Like we gathered 500 counts. What's the statistics of that 500 counts? So this is the formula for a series of counts. So when a lot of times like a physicist or something will come in and they're doing measurements on your cameras, what they'll do is they'll gather a series of counts. So they'll gather like a 500,000 count image, they'll gather another one, another one, another one. And so they'll have a set of series of counts, and then they need to perform standard deviation on those sets to do some quality control or whatever, or adjustments they're doing on your camera. So in that case, it's a little different. And so I wanted to at least show this to you because it's going to help us understand chi-square a little bit, or at least lead into it. But in this case, a standard deviation of a series of counts is going to be standard deviation equals plus or minus the summation of the mean divided by the summated mean squared over the number. So again, don't worry about that too much. I wrote that up here. The mean squared, the square root of the summation of mean squared divided by the number of measurements in the series. Okay. So they would do that to perform tests. The reason I brought that up is because there's something similar we're going to look at when we talk about something called chi-square. Now, first, what I did is I actually went through and did the math on a set of counts using that standard deviation. And so I'll show you that first. So this would be like, so here's, you have like your observations. Okay. So this is the number of times that you did a set of counts that you're measured on your camera. So here's the number of counts, which represents that X. And then here's the deviation of those number of counts. Okay. And then there's the square of deviation. So if you put this formula and you did those measurements, I summed them and I got the mean and everything, and I ended up with this large number divided by 10, which was the number of counts. And I got this number here, 211,562, and then I just did the square of that. And so I ended up with plus or minus 485. So of all these sets of counts, it's plus or minus 485. And then what a physicist or someone that's measuring would do is they would have some standard range that's supposed to be in whatever test they're doing. And then they would take that number and compare it and say, okay, is plus or minus 485 within the range that I expect this camera to be functioning at? And they would have some statistic they could look at and say, yes, it's within the range. Okay, so that's kind of the basic idea. Now, the other principle that the boards mentions, if you go on the boards list and you see what's on there from ARRT, they mention chi-squared. They don't say what about it. They really don't say much. I've never known a student that went and had to perform a chi-square equation. And so based off that, I've gone with, let's teach you what chi-squared is so that you understand the basic of what it is. And then I think most of the questions on the board would just be an idea of what is chi-squared and what do you do with a chi-squared number if you were able to do the equation, right? So hopefully I can make sense out of that. But essentially chi-squared is going to be, again, the summation of the number of counts, subtract the deviation, squared, all over again the mean. So the deviation is the mean, right? So the mean again. Again, don't worry about this. You're not going to have to calculate it. But I took this data and I put it through chi-squared, and I got this number of 298.65. So if you were doing a chi-squared test, there's something called a chi-squared table. And there's one in the back of your Waterstream book. So that's the next slide over here is a chi-squared table. I have the 8th edition listed here. I think it's like 1 or 2 pages different in your new text. But what you do is chi-squared, for something to be accurate according to a chi-squared table, the number needs to be between 0.1 and 0.9. So what that means is you come up here and you have this 0.005, 0.01, all the way up to this 0.1, and then all the way up to 0.9. So accuracy is within these 4 columns. So what you would do in our case is we did 10 counts. So this is the number of counts that you do. We did 10 counts, and remember I came up with this number of 298.65. So we go to our 10 counts, and we're going to go to where we're between 0.1 and 0.9, and we have a number from 4.8 to 16. So we got, what was it, 298, so we're way out, right? So this didn't pass the chi-squared test. It would need to be within that range. What this is a measurement of, so let me kind of distill that down. This is just a measurement of not just machine accuracy, but specifically the part of your machine or the computerized part of it that counts. So it's the counter within your machine, and that could be a well counter, that could be your gamma camera, that could be your thyroid probe, anything that counts. Just remember that it's the counting machine accuracy. Chi-squared is counting machine accuracy. Okay, so I would understand that basically at basic principle. That could possibly be the type of test, like what does chi-squared measure? It measures counting machine accuracy. The other part I would say, again, you don't need to know the equation and how to run it, but maybe understand this, that if you were to look at a chi-squared table, accurate data is between 0.1 and 0.9 on the table. I would say those 2 things are probably your takeaway. Again, this is the way I've kind of taught it for 6 or so years, and everybody's been okay on the boards. But again, ARRT lists chi-squared. It just lists it, and it says nothing else about it. And unfortunately, ARRT doesn't share specifics with us. That's all they give us. So that's what my takeaway. Again, you don't need to understand the equation and how to perform it, but let's understand what it is, and maybe just this number of, when I look at a chart, that's my accuracy. Okay. And I've kind of listed some of that right here. Measure of counting machine accuracy and a 0.1, 0.9. So this I listed just to, again, separate the 2 concepts. Standard deviation or standard errors measures the randomness or intermediate errors or random nature of radioactivity and gets us accurate. And chi-square measures system or determinant errors or measures detector the precision of the counting machine. On here, I just put, like, generally our errors in image are going to come down to, again, to drive this point home, number of counts, the ability of the machine to do what it's supposed to be doing, and then obviously human error, right? But this is why we cover statistics today, really, is these first 2. Is our errors are going to come from either we don't get the counts, something's wrong with our machine, or obviously, like, we did something wrong with our patient or gave him the wrong dose or put him in the wrong position or whatever, our own human error. But these are the 2 things we can easily get out of the way. And then the last thing, this is covered in the book, and so I threw it on there. It's not necessarily specifically related with statistics, at least the discussion we've had, but the book proposes the difference, that what's the difference between sensitivity and specificity. You'll hear I've heard, cardiologists and radiologists talking about how sensitive or specific a test is. And they're kind of hard concepts to understand, but sensitivity is the probability of a positive test, or it's the percentage of fraction of a patient that's ill, they have the thing, and that test can show that they do have that thing. That's a sensitive test. So a less sensitive test might be like, well, we know they're sick in a certain way, but we don't know what it is. Whereas a sensitive test is like, we can show positivity and that patient is ill. We've proven a positive test. And then specificity is the probability of a negative test. So this is patient that's good, that is well, and this test can show a negative test. That's specificity. Again, I don't know that I would go too much deeper than kind of that basic understanding. And you may or may not get a question on that. I honestly don't know. It's one of those things in the book that it went over, so I included it. More than that, I don't know too much, but I'll give you that. Okay, I am done. Is there questions? It looks like Ashley, thank you. I just noticed in the chat you put in the 9th edition the charts on page 665. That's the chi-squared table. If you want to look at it, I'll get that updated. But okay, that's a lot I threw about you. Again, with statistics part, it takes time to explain, but just kind of remember some of those basic principles in understanding why we do what we do in nuke med. And then let me know if you guys have any questions. Again, your test isn't available right away. I'll try to have it available by tomorrow. Let me know if you have any other questions about anything else. And then I will try to get these 2 videos uploaded and on here so you can review them. And hopefully we didn't lose anything on that first half. If we did, I'll let you guys know and we'll figure something out. Maybe I'll get on here and lecture the first half on my own and put it on or something. So, okay. Well, if nobody has any more questions, then
Thank you.
Get out of here. You're welcome.
Hold up. It looks like there's a question that got asked, I think accidentally as a direct message to me. Can you explain that as how it relates to the myocardial perfusion test sensitivity versus specificity from Jesse?
Okay. Let's go back here. I'm going to reshare again. So Jesse, are you still on?
His audio is broken.
Oh,
but it looks like it.
So can you explain that relates to a myocardial perfusion test sensitivity versus specificity? I can try. I don't know if I fully understand your question, but I am going to try. Hang tight. Whoops, I just shared everything. Okay, let's go back to our screen and try to get some definitions. All right, so with a myocardial perfusion scan, we want to talk about sensitivity and specificity. I've not been asked that question, so I'm going to think through. If you have anything else, Jesse, that you mean by that, let me know. Let me widen you up so I can see. So sensitivity, probability of a positive test. What I can tell you is that I know with SPECT, I have heard before that it has a 68% sensitivity. So like 68% of the time, a positive test is positive and it's accurate. PET, I know, has taken that up into the 90s. Now, I can tell you, I know at least internally at Intermountain, they ran studies based on our heart data. And what they did is the numbers they ran is they took a SPECT scan, a SPECT heart, and they took a patient who had a positive scan, and then they took that positive scan and they followed, these are patients that had a positive scan and then went to the cath lab and then indeed had a positive test. And those patients, at least internally and this was Intermountain in Murray is the busiest hospital in Utah, so they had a lot of numbers. This isn't a few patients, this is thousands. And they did those comparisons, and that's where I think they ended up around 68% that indeed there was a positive test on our end, and then they went to the cath lab, and yes, that whatever existed there, and there was something going on. So that I can speak to the sensitivity that way. When they did the same markers, once we started doing PET and we'd been in a few years and had enough data, we did the same markers and we ended up in like 94% or something like that with PET. So I can at least speak to the sensitivity of difference between SPECT versus PET. Now, specificity is the probability of a negative test for a well patient. That one I don't know how to explain the data on that specifically. I'm trying to think with cardiac. I mean, I guess you would have the same percentages that are similar. It's just we're asking about the difference between a positive test and a negative test of the sensitivity. It's sensitive enough to detect it. I guess specificity is probably more like if this test shows that it's negative or that they're well, does it show specificity of what we're negative of? In other words, when you do a cardiac stress test and it comes up negative, we're saying that you are negative for myocardial perfusion. We can't say that you're negative for a different type of heart condition. That's probably how I would explain specificity. It shows a negative test, but it's negative for a specific thing. Does that make sense? I don't know if that helps, Jesse. I wish you could talk. Yes, thanks. Did it. All right. Awesome. Any other questions? This is good. Okay, I'm not seeing anything going on in the chat. All right, I'm going to end it. Y'all have a good one.